So in the last class, we were looking at this problem of variable length lossless compression, but our goal is really to design low complexity schemes, things that can actually be implemented in practice. All right. So the setup that we are always working with is we have a source sequence of length n. For now, we'll assume that the source sequence is IID distributed according to some px. So it's a memoryless source. And we want to come up with a variable length zero error compression scheme. And we'll now assume that both the length of the sequence, well, the length, maybe not the length of the sequence, but the distribution is given to us. Okay, so px is known, but the actual length of the sequence may or may not be known beforehand. Right? So we are going step by step by relaxing the assumptions. Initially, when we looked at the optimal lossless compression scheme, we assumed that n was known, px was known, we didn't have any computational complexity constraints. But now we are saying that firstly, we do have complexity constraints. I don't allow you to design really hard encoding and decoding schemes. And further, I tell you that n is not known beforehand. So whatever scheme you give me, it has to work for all n, a generic framework. So for this, it's helpful to restrict ourselves to symbol-wise compression algorithms, wherein the encoding of a sequence of length n is just the concatenation of the encodings of the n individual symbols, right? So then it boils down to just designing the encoding for one individual symbol. The complexity is not too much because the overall complexity of encoding x1 through xn is just n times the complexity of encoding one particular symbol. Right? The decoding complexity may be a little bit harder depending on how you design it, but at least the encoding complexity is just going to be n times the complexity of decoding n symbols. So the complexity is just order n. Right? So then how do you design a good compression scheme for individual symbols? Now our optimal compression scheme that we saw earlier doesn't work anymore because once you concatenate code words, there's no guarantee that you'll be able to recover the individual symbols after concatenation, which means that you need to impose some more restrictions if you want to do symbol-wise compression. So towards that, I defined a few notions. Firstly, I said that a compression scheme is non-singular if two code words or two compressed sequences corresponding to distinct symbols are also distinct. So if x is not equal to x prime, then the encoding of x cannot be equal to encoding of x prime. And I also defined the extension, which is essentially what we wanted, right? The encoding of x1 through xn is just the concatenation of the encodings of x1, x2, x3 up to xn. And really what we are interested in is designing codes that are uniquely decodable. That is, from the extension, you should be able to recover the stream of source symbols. And for that, the basic requirement is that the encoding of x1 through xn cannot be equal to the encoding of some other x1 prime up to xn prime. So the extension of the code should be non-singular. All right. But a further restriction of this is prefix-free codes. We'll see why we are doing a further restriction soon enough. But for us, what we are really interested in is designing uniquely decodable codes. If you give me a good, efficiently encodable and decodable, uniquely decodable code, I'm happy. Okay. But prefix-free codes are nice because they also capture sort of the intuitive notion of sort of non-confusability or non-singularity, in the sense that it's prefix-free if no code word is a prefix of any other code word. So we know for sure that if a code is prefix-free, then it is guaranteed to be uniquely decodable, although the reverse is not necessarily true. Okay. One useful way of thinking about prefix free codes or uniquely decodable or non-singular codes is in terms of the code tree, because it gives a graphical representation of the code itself and a lot of properties of such codes. So given any code, you can always construct the code tree which is basically a binary tree with the left branch being labeled 0, the right branch being labeled 1, and the nodes and some of the nodes are going to correspond to source symbols. So the code or the code word for a particular source symbol is obtained by traversing the tree from the root to that particular symbol and reading the edges that you traversed along which to get to that particular symbol. Okay. And so this was the code tree for the prefix free code for this particular example prefix free code, right? And for a prefix free code, the code tree is such that can one of you please turn it on? Can you also turn off the fan, please? Is this okay? Okay. Thanks. All right. So as I was saying, you can for any code, whether it's instantaneous or uniquely decodable or non-singular, many of its properties can be derived or can be intuitively understood by looking at the code tree and studying the properties of the code tree. So for a prefix-free code, the code tree has the property that no source symbol is a descendant or an ancestor of any other symbol. All right, which translates to saying that no code word is a prefix of any other code word. For something to be non-singular, it basically means that no two symbols correspond to the same node, right? And unfortunately, properties of uniquely decodable codes can't be directly interpreted in such a nice way. The only way you can understand the properties of a uniquely decodable code is by looking at all possible extensions. All right. But the nice feature about prefix-free codes is that the extension for, let's say, two symbols can just be obtained by appending code trees to get, let's say, the length 2 extension. Let's take this example. So this is a prefix-free code. If I want to encode one particular symbol. Now, what would be the code tree if I wanted to encode pairs of symbols? All right. So one way of obtaining that corresponding code tree would be the following. It's a bit hard to draw because it's quite messy. So what I basically did was I took 4 copies, or essentially 5 copies of the same code tree, and then at each leaf node, I attached one of the trees. Correct? So really, if you think about how you would encode the prefix-free code, you would have started with the root and then traversed along the edges to reach a particular node, and then restart from the root to encode the next symbol. Correct? What that means is basically if you take another copy of the tree, attach the root to one of these symbols, then you get the code tree for encoding pairs of symbols. And likewise, for triples of symbols, you would attach another copy of the tree here, 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 and so on. So you see that the tree is like growing in size. Okay, but this is a property that's inherited only by prefix-free codes. This, for example, does not hold for uniquely decodable code in general. All right. So you have all of these nice properties that hold true for prefix-free codes. Any questions so far? Okay. So what's our goal? Our goal is to design a uniquely decodable code with the minimum expected length. So given a distribution Px, we want to design a uniquely decodable code
Prefix-free code tree is also non-singular.
Correct. Every prefix-free code is non-singular, but the reverse is not true. Any other questions?
Reverse is not true.
Correct.
You want an example?
Okay, you want an example? I'll come to that in just a minute. Okay, so this is our goal, right? Our goal is to design a uniquely decodable code with the least expected length. So as I was saying, every prefix-free code is uniquely decodable. Hopefully that is clear. Everybody agrees with that particular point. But not every uniquely decodable code is prefix-free. And here is an example. Let me. Right, let's see if I can come up with a simple example. Okay, let's take the following. Say it's a trivial example, okay, which doesn't really give any compression, but you can come up with examples that give you compression. So it's basically the following. Assume that there are just two symbols. Symbol A is going to be encoded to 0, and symbol B is going to be encoded to 0, 1. Clearly this is not prefix-free. Okay. This is an example. I agree, this is a suffix-free code. But you can also come up with examples which are not suffix-free. So in this case, it is not prefix-free, but you can see that no code word is a suffix of any other code word. So when you encode, you will be encoding it from left to right, But a simple way of decoding it is to decode from right to left. So for example, let's say I have some sequence A, B, A, B, A. This would be encoded as 0, 0, 1, 0, 0, 0, 1, 0. Right? So when encoding is the standard approach, you just read the code table and then output the code words in sequence. But when decoding, I can't just do that because I read from the left, I read a 0. I'm not able to, at this point, I'm not able to decide whether the next symbol is, whether the current symbol is A or it's just the first bit of B. I read the next symbol, I see that it's another 0. Again, I'm not able to say whether this is AA or AB. I read the next symbol, I get a 1, which must mean that the first symbol must have been an A and the second symbol must have been a B, and so on. All right. So this is a simple sort of a trivial example of a uniquely decodable code.
Is
Yeah.
also the optimal encoding uniquely decodable code, which is not like if you take the whole string to decode the whole thing, then it is.
So is your question that, so I have the class of, I have the class of non-singular codes. And within this class lies the class of uniquely decodable codes. And within this class, there is a class of prefix free. And clearly they are strict subsets of each other. So if my goal is only to minimize the expected length, I know that when I impose the uniquely decodable constraint, potentially the minimum expected length that I can achieve could be larger, right? But when I go from uniquely decodable to prefix free, is there a loss in the expected length? Is that your question? That is, the minimum expected length that I can achieve using the best prefix free code, is it going to be larger than the minimum expected length that I can achieve using the best uniquely decodable code? Was that the question?
No, I was like the example of the uniquely decodable code.
Okay, so this example here, okay.
Yeah, no, like the optimal encoding speed is also that, like, because like if you decode by taking the whole string, it is uniquely decodable.
I'm not sure I quite followed the question.
Okay, like if you know the fixed length or like the maximum length of your string,
Okay,
you could take the whole string
yes.
and like the whole encoded string and decode based on the whole string to get the using the optimal coding.
Again, what do you mean by the optimal coding
No,
scheme?
like you assign 0 length to the maximum probability string.
Okay, so you're saying that if you knew the length of the source sequence,
Yes, or like the
then
maximum length.
maximum length, but then the optimal code that we saw earlier, that is not uniquely decodable, right? Because you just concatenate the, I guess, this very example says that these are two source sequences of the same length. You know that the source sequence is of length 2, but if you see the code words, both of them have the same encoding. Right? See, so even knowing the length doesn't allow you to decode the source sequence if you use the
We were
optimal.
to not use the 0 length, 0 length symbol, it would be possible.
Even then you would run into issues for larger alphabet sizes. Again, by the prefix, because you're not satisfying these prefix free constraints. So for example, let's assume that you never see an A, okay? Suppose my code table is just this. Then, for example, you would not be able to distinguish between BD and DB. Right? The encoding would be 0, 0, 0. Right? So BD and DB, this is 0. So this would be 0, 0, 0. This would also be 0, 0, 0. So you can never distinguish between it. All right? So it's a lot more than just removing the empty string.
So about the question you asked, could you go to the
No. Here.
the optimal expect that does it increase from infinity equal to
That's what we'll see in this class. Okay.
from non-singular to uniquely equal to it doesn't.
It does increase. We'll also see that in class. All right. But at least it should be clear that the optimal code doesn't work in this. It's not uniquely decoded. All right. Okay. So what we saw in particular for if we didn't care about unique decodability, we could achieve an expected length which is less than or equal to the entropy. Okay. And it was lower bounded by entropy minus something, some function of entropy. Right. So the goal in this particular class will be to first find out bounds on the minimum expected length for uniquely decodable and prefix-free codes. Okay, and see if there's some kind of reduction. Any other questions?
Does the best uniquely decodable code have to be prefix-free?
Best in terms of minimum expected length?
Yeah.
That's what we'll see later on. That was the question. So if you compare the expected length of the best uniquely decodable code, is it going to be less than the expected length of the best prefix-free code or not?
So whether it's less or not.
The best uniquely decodable code could be different from the best, need not be prefix-free. Okay? But there could be a prefix-free code which has the same expected length as the best uniquely decodable code. We're not ruling that out yet. Okay? But because we know that there are uniquely decodable codes that are not prefix-free. Okay? But certainly if we have prefix-free codes, okay, I'll come to that point later. Any other questions? Okay. So far for a given symbol x, we have, for any given code, the encoding was denoted ENC of x, and the length of the encoding was L of ENC of x. Right? Just to simplify notation, I'll use L of x to denote the length of the encoding. Okay, because I don't want to write ENC over and over again. So first we'll derive some bounds or some properties of any general prefix-free code and any general uniquely decodable code. Let's say L of x. So this inequality says something about the code word lengths of any general prefix-free code. It's a necessary condition that any prefix-free code has to satisfy. So take any prefix-free code. It doesn't have to be optimal at all. Any general prefix-free code. You take the set of code word lengths. In this particular example over here, I had L of A to be equal to 1, L of B was equal to 2, L of C was equal to 3, and L of D was also equal to 3. What is summation 2 to the power minus L of x in this case? This is 1 by 2 to the power 1, which is half, plus 1/4, plus 1/8, plus 1/8, which is exactly 1. Right? The claim is that for any general prefix-free code, the sum is going to be less than or equal to 1. I'm sorry?
When does the equality satisfy? Is it because if it is optimal?
Not necessarily. There are a large number of conditions where it need not be satisfied. Right? But we'll see that in a sense, it is codes. If it is not satisfied with equality, then if it is bad, then it's definitely not going to satisfy with equality. Right? So here is an example of a prefix-free code that does not satisfy this inequality with equality. So I have two symbols, A and B. It's again a very simple toy example. This code is obviously prefix-free. So this quantity, which is called the Kraft sum, in this case is half plus 1/4, which is strictly less than 1. Right? So this quantity is called the Kraft sum. So I haven't completed the statement yet. So this particular result says that for any prefix-free code, this should happen. The code word lengths must satisfy Kraft's inequality. Also, if I give you a set of integers, all right, say I take L1, L2, L3 up to Lm, which satisfy Kraft's inequality, then there exists a prefix-free code with those code word lengths. All right. Questions?
Does this hold for the code words which are made for not individual symbols but for a bunch of
So right now we're looking at encoding of, you fix the alphabet and you construct the code for that particular alphabet. All right. But this also holds true, say, for length 2 and length 3 extensions, because if a code is prefix free, then the length 2 and length 3 extensions are also going to be prefix free. All right. That's a property that is inherited. So even those will satisfy Kraft's inequality for a particular length. All right. You can only combine, say, k symbols at a time. You can't say you can't combine one symbol and two symbol and three symbol and four symbol and so on together. The proof is fairly intuitive. I'll give. Yeah.
What is the other statement? Converse.
So if I give you a set of lengths, all right, or if I give you a set of integers L1, L2, L3 up to Lm, which satisfy Kraft's inequality, that is summation 2 to the power minus Li is less than or equal to 1, then you can construct a prefix-free code with exactly those code word lengths. Okay. All right. So I'll give two proofs of this particular statement, or at least the first part of the result. One is going to be a more visual proof. The second is going to be a probabilistic proof. The visual proof is just this. We know that any prefix-free code can be represented in terms of a code word tree. Right? Let me go back to the example I had, or let's draw it again. Right, so I had this code word. So suppose I have this code word tree. The lengths are 1, 2, 3, 3. I'll construct the depth 3 complete binary tree in this case. And for each symbol, each source symbol, I'll count the number of descendants which are leaves. All right. So in this case, the symbol A has 4 leaf descendants. Symbol B has 2 leaf descendants. Symbol C has 1 leaf descendant, which is itself. And symbol D again has 1 leaf descendant itself. Okay? Is that okay? Is that clear what I mean? So basically I'll construct, okay. So we fix a particular alphabet. Let L max be the maximum length. Okay. Construct the complete binary tree. Of depth L max. The code tree is a subtree of this. Right? In this case, this is the code tree, whereas the whole thing is the complete binary tree. So for each symbol x, let us count the number of descendants which are leaves. Remember, this is a prefix-free code, right? So no code word or no symbol is going to be a descendant of any other symbol. So if you take any node that corresponds to a source symbol, everything below it is not going to be a part of the code tree. Do you agree with that point? All right. So if you take any symbol, everything that is below it, all the descendants are not going to be code words. So it's not going to be a part of the code tree. So what will be the depth of the subtree below a particular symbol if the symbol has code word length L of x? It will be L max minus L of x, right? So basically the subtree below it is going to be a complete binary tree of depth L max minus L of x. Correct? So how many leaf descendants is this going to have? It is just going to be 2 to the power L max minus L of x. Okay. Is this okay with everybody? Okay. So firstly, what are the properties that this code tree has? I've constructed the complete binary tree. The code tree is this particular subtree of it. I know that if I take any node that corresponds to a symbol, the rest of the tree below that particular symbol is not going to be part of the code tree. That comes because of the prefix-free property. All right? But what can you say about the subtree which is described by all of the descendants, everything that is below a particular node? It is going to be, since it's a complete binary tree, the subtree is also going to be a complete binary tree. But what is the depth of this particular subtree? You know that the total depth is L max. The depth, symbol A, is at level L of A. Right. So what is the remaining depth? It is just L max minus L of A. In general, it is L max minus L of x. And you know that everything below it is a complete binary subtree. So the total number of leaves of this subtree is going to be 2 to the L max minus L of x. Okay. So for any symbol, the number of leaf descendants is 2 to the power L max minus L of x. And again, because of the prefix-free property, if I take any two symbols, the descendants are all going to be distinct, right, by the prefix-free property. Two symbols cannot have any common descendants. So the total number of leaf descendants is summation over all x in x 2 to the power L max minus L of x. This is the total number of leaf descendants of all possible symbols. Correct? But since the set of leaf descendants can't intersect, they're all distinct, this can be no more than the total number of leaves in the complete binary tree. But how many leaves does the complete binary tree have? 2 to the power L max. Alright. Now if I divide both sides by 2 to the power L max, I just get summation x in x 2 to the power minus L of x is less than or equal to 1. And that's Kraft's inequality. Which one?
Just last.
This one. Okay. So for a given symbol, this is the total number of leaf descendants. This is the number of leaf descendants, right? So the total number of leaf descendants is summation is basically the left hand side. But because of the prefix free property, something that is the descendant of one symbol cannot be the descendant of any other symbol, right? So the total number of leaf descendants cannot be any more than the total number of leaves in the complete binary tree, right? So the sum of this, and this cannot be any more than the total number of leaves. But the total number of leaves is 2 to the power L max. That's how we get the right hand side. It may not be equal, right? Potentially, if you take this particular example over here, right? In this case, symbol A has 4 descendants, symbol B has 1 leaf descendant, but this is not all of the possible leaves of the complete binary tree. Right? So in this case, Kraft's inequality is not satisfied with equality. Yeah.
Yes, we are considering only the leaf descendants, not
Correct.
the complete size of the subject.
No.
So this is primarily because it is a prefix-free setting, or like is there some other reasons?
Well, in the end, it's a proof technique, right? I just wanted to show that this inequality was true.
No, because like if it's prefix-free, then it only makes sense if we take the leaves and not like it can't become equal between the two.
I mean, so you can count the total number of descendants, but in general, I can't say anything about the total number of descendants. So basically, I want to say something about the right-hand side as well, right? But then I would be overcounting the number of descendants, which would not give me anything useful. Because all of the code words can be at different levels. Right?
So, the inequality is when you extend the tree, you don't have a full binary.
I'm sorry?
The inequality holds strictly
Huh?
holds when you extend the tree and you don't have the entire binary.
Correct. Yeah. That's true. Okay, so this was one proof. There's another probabilistic proof. Let's say I consider the following Bernoulli process. So basically, I generate a random sequence of bits 0 1 0 1 1 0 1 1 1 1 and so on, and this Bernoulli half process can potentially continue on forever, but it is going to stop when you see a valid code word. All right, so you start, right? So 0 1 0 1 1. If so, at each step, if this corresponds to a valid code word, then I stop. If not, I generate another ID Bernoulli half bit. All right. If this is a valid code word, I stop. If not, I generate another Bernoulli half bit, and I keep continuing. Okay, that's the process. Is this process clear? What the random experiment is? So you're given a code, and independent of the code, you start flipping bits, and you stop only if the string that you have seen so far is a valid code word. Potentially, this process can go on forever, doesn't matter. Okay, that's the random experiment. All right. So, I'm sorry?
What if you miss a code word?
What do you mean miss the code word?
Like, you have reached a point where how many ever points you that you don't reach the code word?
Yeah, then you just go on. It goes on forever. Okay? But if, let's say, some part of this is a valid code word, then you stop at that point. You don't proceed any further. So you stop only if what you've seen so far is a valid code word, and if not, you keep continuing. All right? So this is some experiment. What is the probability that this will give you a particular code word? So let me call this X star. Okay, or maybe let me call it C star, because this can potentially be an infinite string. So what is the probability that C star is equal to the encoding of a particular symbol X?
See, you're stopping only when you see a code that matches C, not the extension of C.
No, not extension, because it's prefix free. Anything that is the extension would have to be, you would have already have had to see a code word before that.
We are considering a general setting.
So this is a prefix free code. I'm assuming that this is a prefix free code. All right. So the encoding of two symbols is the concatenation of the encoding of the two symbols. Right? So which means that if I had to see the encoding of the pair, I would have already have had to see the encoding of the first symbol anyway. Right? I would have stopped by then. Okay, so what is this probability? What is the probability that this process gives you the encoding of one particular symbol X? It is 2 to the power minus L of X, because the encoding of X is it's some string of length L of X, and since these are ID Bernoulli half bits, the probability that it is equal to this particular sequence is 2 to the power minus L of X. Okay? So what is the probability that this process terminates? In other words, what is the probability that C star has finite length? It is basically sum over all X 2 to the power minus L of X. Correct? Is this okay? Great. But this is a probability, so it can't exceed 1. Right? So this quantity is greater than or equal to 1. And that's all. Right? So summation 2 to the power minus L of X can be at most 1. So this is a probabilistic proof for the same inequality. So this is a much shorter proof than what we saw earlier. But the earlier proof had the nice property that you also analyze some properties of the tree. So it gives you some more intuition into the properties of the code itself. Whereas this doesn't. This completely throws out all of those things. Which one? So the probability that C star terminates, so C star will terminate only if you see some symbol, right? Or the encoding of some symbol. And the encodings of the symbols, again, we're assuming the prefix free property. If you see the encoding of one symbol, then there's no chance that further on you will ever see the encoding of any other symbol because of the prefix free property. So the probability that C star terminates is the probability that C star is the encoding of some X, right? Which is, again, these events are disjoint. So it's equal to the sum of the probabilities that you see the encoding of X1 or X2 or X3 or A or B or C or D and so on. Okay. Note that this doesn't work if it is not a prefix free code, because then C star is equal to encoding of X. In this case, we assumed this happens because of the prefix property. And the other property is that this is precisely the probability of seeing the encoding of X. If it is not prefix free, let's say that one code word is a prefix of some other code word, then you would never see the code word that is an extension of the other code word, right? For example, say this is A, B, C, and D. Okay, let's consider a code tree. This is not a prefix-free code. The probability that you see the encoding of A is half. The probability of seeing the encoding of B is half. But the probability of seeing the encoding of C is 0. Because you will never see C. If you see, because you would have already seen B previously and you would have terminated by then. Right? So we're crucially making use of the prefix-free property here. Is that clear? Any questions? Okay. So this is one half. That any prefix, this is a necessary condition that any prefix-free code must satisfy. Now let's look at the converse. So given any set of code word lengths, we can construct a prefix-free code. And again, it's the intuition basically comes from the first part of the proof. Right? So if I give you a set of code word lengths which satisfies 2 to the power Kraft's inequality, then you always run the following procedure. For the first symbol, so you construct the complete binary tree of depth L max. Okay, you construct the complete binary tree of depth L max. You start from the root. Let's say you order the lengths in a decreasing or non-increasing order. Okay. So for the first code word, you start traversing down the tree and you keep going to the left every single time. All right, until you hit L1. You go up to depth L1. All right. So in this case, I started from the root, and let's say that L1 is equal to 2, L2 equal to 3, L3 equal to 3, and L4 is equal to. Is there a question?
L1 is greater than
Okay. I'm sorry. I wanted it to be the other way around. So L1 is less than or equal to L2, which is less than or equal to L3, which is less than or equal to Ln. Okay. I sort them in ascending order. Okay. So L1 is 2, L2 is 3, L3 is 3, and L4 is 3. Just as a toy example. So I start from the root. and I keep going to the left until I reach depth L2. I reach the depth of L1. In this case, it is depth of L2, and I stop there. All right. That is going to be the encoding of the first symbol. So this is symbol 1. And then from this tree, I delete all of the descendants. All right, so I'm going to just I'm going to delete all of the descendants of this particular subtree. And now I again go back to the root for the second symbol, and I keep traversing to the left, but if the descendant is already occupied by some other symbol, I move to the right. Okay, so if I have already traversed down everything that there can be traversed to the left side of the tree, I go to the right. So I start from here, I go to the left, I see that there's some part of the subtree below that has not been visited so far. So then I explore the right half of this particular subtree. And from here, I know that everything below has not been explored so far. I have reached this particular point. I have not visited anything so far. So I will visit the left half. Okay. So it's basically you're exploring. You think of it like exploring a maze. And you're always going to go to places that you have not visited before. So you start with the root. If everything to the left has already been explored, then you don't go there. Then you go to the right. If the left half has not been completely explored, then you go to the left. So I started out with this particular point. Not everything on the left has been explored as of now. So I go to the left. At this point, I sit at this particular node. Everything to the left has already been explored at this point. But not everything to the right has been explored. So I go to the right. And then I come to this particular node. The length is equal to 3, so I need to go up to depth 3. So far I have only gone to depth 2. Now I look below this. I have not visited anything. I have not explored anything below this as of now. So I go to the left. I've reached depth 3 at this particular point and I stop. Okay. So I get. So this is going to be my encoding for symbol 2. And then I again, for the next symbol, I again start with the root. Has everything to the left been explored so far? No, right? Because this part has not been explored so far. So I go to the left, and then everything to the left of this part has already been explored. So I go to the right. Everything to the left of this part has been explored. So I again go to the right. I've reached depth 3, so I stop. All right, and I delete everything that is below this. I declare that everything below this has been explored. So this would give me the encoding of symbol 3. Now for the fourth symbol, I again start from the top. Now at this point, everything to the left has already been explored. So I go to the right. This is depth 1. Everything below this is unexplored, so I go to the left. Everything below this is unexplored, so I again go to the left. At this point, I have reached depth 3. And at depth 3, I stop and I delete everything below this. In this case, there's nothing to be deleted. All right, and then I stop. So this is going to be the encoding of symbol 4. Okay. Now, why is this guaranteed to work? Right? Why this is guaranteed to work? So, firstly, you agree that this is going to give me a prefix-free code. If this somehow works, then at the end of it, I am going to have a prefix-free code, because the traversal is always in such a way that once you use one node as the encoding of some symbol, you have removed everything below that. So anything below that cannot be a valid encoding of any other symbol. So this process is guaranteed to give me a prefix-free code. But firstly, is it guaranteed to work? In the sense, what if at some point there's nothing to traverse anymore, right? That can potentially happen. Maybe I have already explored everything and there's nothing left to explore. But that won't happen because what is the size of this particular tree? It's of depth L max, correct? And at each stage, I am deleting a portion of the subtree. But how many nodes am I deleting from the subtree? If I count the number of leaves that have been deleted from the subtree, that is going to be 2 to the power L max minus L of x. Right? So every time I'm giving the code word for a particular symbol, I'm removing 2 to the power. So every time you give a code word, say of some symbol x, you're deleting or getting rid of 2 to the power L max minus L of x leaves. All right. So you will have nothing left to traverse or nothing left to explore if you have deleted all of the leaves in the tree. All right. From that point onwards, there'll be nothing left to explore. Correct? But that is not going to happen because the total number of leaves you would have to delete in this particular process would be 2 to the power L max minus L of x, which is guaranteed to be 2 to the less than or equal to 2 to the power L max, because the code is guaranteed to satisfy Kraft's inequality, or the set of code word lengths is guaranteed to satisfy Kraft's inequality. Right, so this gives us a systematic procedure to come up with a prefix-free code. As long as you have a set of code word lengths that satisfies Kraft's inequality, there is an algorithm that you can just follow and design a prefix-free code for that set of code word lengths. Okay. Any questions? So one assumption that we made in this proof was that the source alphabet was finite. All right. But in fact, this can be extended to infinite alphabets as well. You can find a proof in Cover and Thomas, but I won't really spend time on this. Sorry?
Can't you represent everything from 0 to 1 using code?
But it has to be prefix free, right? I'm sorry, maybe you can, what is the question?
Every number
you can represent every number from 0 to 1 using?
Or you have the lines in the binary infinite.
Okay, I didn't get the question.
Still Kraft's inequality would for this
For uncountably infinite, what do you mean?
can't every number from 0 to 1
Yes,
be represented using the code.
but can it be represented in a prefix-free form?
It's prefix free, but it's an infinite for each code word is
I agree, you can represent, say, the interval from 0 to 1, for example, using an infinite sequence of bits. But we're specifically looking for, again, what does it mean? We're particularly interested in designing variable length, zero error, lossless compressors, right? Which means that the encoding for a particular symbol has to terminate at some point, right? With sufficiently large probability. It has to terminate eventually, which is not guaranteed if the alphabet is continuous, right? For almost all symbols, it is never going to terminate. And you can't really have zero error if you have uncountably infinite alphabets anyway. Any other questions? Okay. It turns out that every uniquely decodable code also has to satisfy the same inequality. Note that not every uniquely decodable code is a prefix-free code, but it still has to satisfy. The code word lengths must satisfy the same inequality. All of these are properties purely of code word lengths, nothing else. But really code word lengths are what we are interested in, because in the end the goal is to minimize the expected code word lengths. So if I have a basic property of the set of code word lengths, then I can also say something about the expected length, because that's corresponding to a particular distribution, right? So far, when I'm talking about Kraft's inequality or the Kraft-McMillan inequality, I don't really care about the distribution of the source. You're giving me some code, it doesn't matter what the expected length is. Any code, any prefix-free code, just that prefix-free constraint or just that unique decodability constraint automatically imposes these constraints on the code word lengths. And it turns out that both for uniquely decodable as well as prefix-free codes, they have to satisfy the same constraints on the code word lengths. All right. This proof is not as intuitive as the previous approach, but it's not too hard either. It essentially uses the idea of generating functions. So let's say I'm given a particular code. So given a code C, I'll define, say, GC of x, let me call it GC of z, which is a polynomial, all right, and this polynomial is essentially summation over all x in x z to the power L of x. So, for example, when I had the encoding 0, 1, 0, 1, 1, 0, 1, 1, 1, for this particular code, this GC of z would be z plus z square plus z cube plus z cube, which is z plus z square plus 2z cube. Okay. So that's this polynomial that I defined. That's GC of z. This is equal to, I can also write this as summation, say L equal to 1 to L max AL C Z to the power L, where this ALC is essentially the number of code words of length L. In this example over here, there was one code word of length 1, one code word of length 2, and two code words of length 3. These are two different ways of representing the same thing, or in other words, two ways of counting the same thing. The nice property about polynomials is that just from this, you can say something about the lengths corresponding to extensions. So let's say I combined case symbols. What would be G CK notation? I combined the encoding of case symbols. I claim that this is nothing but GC of x whole to the power k. So in other words, let's take for two symbols GC2 of x is nothing but summation overall x in x, let's say x1 in x, z to the power L of x1 times summation x2 in x, z to the power L of x2, which is nothing but summation over all possible x1 in x, summation over all possible x2 in x, z to the power L of x1 plus L of x2. Because we are concatenating the two code words together, this GC2 of x is exactly equal to summation over all possible x1 in x and x2 in x, z to the power of L of x1 plus L of x2, because the length of the code word corresponding to x1, x2 is just the concatenation of the code words corresponding to x1 and x2. All right? But this quantity over here is nothing but gc of x the whole square. Oops. Do you agree with this point? Right? This is gc of x the whole square is nothing but summation x in x z power L of x the whole square, which is nothing but I'm just changing the variable. L of x1 times is this fine?
C corresponds to the binary string.
So C is the code word, is the code. C is the code which is just the encode. So I'm using C to denote the encoder decoder pair. All right. So C is the code on individual symbols, one symbol at a time. All right. C square is the code that corresponds to two symbols. I concatenate two symbols, I get another code which is of longer length. Is that clear?
If your word concatenates multiple symbols in the code,
Correct.
it's the same thing as
That's what we were assuming here, right? It's because we're fixing a C. C2 is the two length extension of C. So
notation-wise, can you write L of x1 plus L of x plus L of x1 plus
you can if you want, but L of x1 x2 is exactly equal to L of x1 plus L of x2 because the encoding of x1 x2 is encoding of x1 concatenated with encoding of x2. All right. So basically, generally, so g ck of x is summation over all possible xk z to the power of L of xk. Right, this is just by definition, but L of xk is summation I equal to 1 to k L of xi, since the encoding of xk is just the concatenation of encodings of x1 up to xk. Right? So this gck of, okay, my bad. So this should be gck of z because my dummy variable here is z. This is summation x1 in x, summation x2 in x, summation xk in x of z to the power L of xk is L of x1 plus L of x2 up to L of xk. Which is the same as summation x1 in x up to summation xk in x times the product I equal to 1 to k z to the power L of xi, which is equal to the product I equal to 1 to k, because I can take the terms out. Each of the summation is over a different variable. The product of each of the product variables. This is equal to summation xi in x z to the power L of xi. But then this quantity is the same for every I. So, okay, is this, up to this point, is it okay? So firstly, we have this particular definition. This is by definition. So hopefully there's no confusion at this point. The next property I'm using is that the length of the encoded version of x1 through xk is the sum of the lengths of the encoded versions of x1 through xk. Because it's obtained by concatenating the strings. Right? So hopefully this is okay. Right? Okay. Then I'm just writing the same thing out over here. That's how you get this. So is this point okay? It is just that, so this is a compact version of representing the summation. This is a more drawn out version of the same summation. Right? So this is equal to summation over all possible x1 through xk of z to the power of summation L of x1 through L of xk. But the something raised to the sum can be written as a product of z to the power L of x1 times z to the power L of x2 times z to the power L of x3 and so on. So I get, so this quantity is basically equal to this quantity. Hopefully that is okay. Right. Then I'm just interchanging the order of the product and the summation, because each term in the product is for a different xi and the summation is also for a different xi. So for example, for this particular summation, I can take out everything that does not involve xk, and I can do that sequentially. All right. Hopefully this is okay. Any questions? Okay. So then I get product I equal to 1 through k of summation xi in x z to the power L of xi. So is this okay up to this point? Now this quantity is the same for every xi. Right? Because xi is kind of just a the I is just a dummy variable. So this is nothing but product I equal to 1 to k sum over all x in script x z to the power L of x, which is nothing but this whole to the power k, which is just gc of z whole to the power k. So gck of z is gc of z whole to the power k. Is that okay? So this is true in general for any code, right? As long as I'm doing symbol-wise encoding, this holds true. Now let's look at gck of z. Let's call this equation 1. So gck of z is equal to summation overall L equal to 1 to, what is the maximum length? K into L max, right? Because the maximum length of the code for C is L max. When I'm concatenating k symbols together, the maximum length can go only up to k times L max. K times L max of the number of code words in CK of a given length L times Z to the power L. Right? This is just another way of writing things. I'm just grouping together terms with the same length. Is this okay? Excellent. So now let's use the property of a uniquely decodable code. When is it uniquely decodable? When the kth extension should be non-singular, right? So in that case, how large can this particular quantity be? How many code words can you possibly have for a given length L? 2 to the power L, right? Because there are at most 2 to the power L distinct sequences. This quantity can definitely be no more than 2 to the power L. Since C is uniquely decodable, CK is non-singular, therefore number of code words of length L, which is equal to AL CK, is at most 2 to the power L. So for any Z and for any K, GCK of Z is less than or equal to 5 minutes. This quantity is less than or equal to summation L equal to 1 to K times L max A 2 to the power L times Z to the power L. But this quantity is also equal to GC of Z whole to the power K. Hopefully it's okay up to this point. This is a polynomial with a dummy variable Z. So this holds true for every value of Z. So let's look at GC of half whole to the power K. This is less than or equal to summation L equal to 1 to K times L max 2 to the power L 1 by 2 to the power L. Question? So I'm using the property that this quantity is equal to this quantity, is less than or equal to this quantity, and I'm substituting Z is equal to half. That's all, nothing else. So this is 2 to the power L times half to the power L, so that's at most 1. So the right hand side is at most K times L max, and the left hand side is summation, just using definition, it is summation over all x in x, Z to the power L, or Z to the power L of x. So it is 1 by 2 to the power L of x whole to the power K. So for every K, 2 to the power minus L of x is less than or equal to K times L max whole raised to 1 by K. This is true for all K. So in particular, summation x in x 2 to the power minus L of x is less than or equal to the limit as K tends to infinity, K times L max whole to the power 1 by K. Any guess what the right hand side is? It's 1. All right, so I leave that as an exercise. Just basic calculus, nothing else. And that's it. So for any uniquely decodable code, the Kraft sums can be at most 1. All right. Okay, so let's stop here.